Hey there, calculus people. Today we are doing section 4.1, which is the chain rule. So what we add on the chain rule is the fact that we have a function inside another function. So we're still doing derivatives the same way, but because we have a function inside another function, we're going to have to change up the end product or quotient, whatever we have with our derivatives. So we will be thinking about it as a composite function, something inside another function, doing it and the power chain rule function, and then differentiating parametrically defined functions. So I know you did parametric functions in pre-calculus. You didn't spend a lot of time on it, but we are going to do parametric derivatives. They're not too bad, so we're going to do that as well. So first thing, chain rule here, it's differentiable. So I want you to look at this. So you have two different ways that we can write the composite function. So g of x needs to be differentiable, composite needs to be differentiable, and f needs to be differentiable. So ideally, what we are doing when we're finding the derivative of either of these is we do the derivative of the outside value, inside remains the same here, and then multiply by the derivative of the inside. So Leibniz here, Leibniz and Newton, they were both fighting over who started calculus, but he was one of them. He writes it like this. So if we have two separate functions, where g is inside f, you can just find the derivative of this one, multiply by the derivative of that one. I just think of it as multiplying the derivative of the outside times the derivative of the inside. So on this example here, an object moves along the x-axis so that its position at any time t greater than or equal to 0 is given by the function s of t equals sine of 5t minus 1. Find the velocity of the object as a function of t. So we're looking at this function right here. It's a composite function. The outside part of the function is the sine. The inside part is 5t minus 3. Okay, so we take 5t minus 3, we would put it in here. These are your two functions you're dealing with. You have an outside function and an inside function. So using the chain rule, we are going to find the derivative of the outside function times the derivative of the inside function. Don't forget that, so what they did is they just said, okay, my inside function is u. I did the derivative of the outside. I multiply by the derivative of the inside, but then we have to replace u back with what the inside was originally. So the inside is still going to be there with the cosine. Outside inside rule, so I've already kind of talked about this, but we want to think about it as finding the derivative of the outside multiplied by the derivative of the inside. So an example of the outside inside function, looking at this right here, my outside function is the cosine, the inside function is 3x to the fourth minus 2. So we are going to find the derivative of the outside, that's negative sine. Inside gets left alone, remains the same, and then multiply by the derivative of the inside. Now, normally I like to put this value in front. They did as well, just so we don't confuse that with being multiplied by what's in the parentheses there. Example of repeated differentiation. So I like to call this the chain rule inception. If you've ever seen the movie Inception, it's a dream within a dream within a dream. This is basically a chain within a chain within a chain. So you have an outside function, a middle function, and then a very inside function. So as I look at this here, my very outside function is going to be that cube root there. Okay. Middle function is sine, and then the very inside function is 2x. So as we think about it, you want to do the derivative of the outside, which is a power rule. So here was the power. Bring the power to the front, the exponent to the front, subtract 1 from our exponent. The inside remains the same. Then we need to multiply by the derivative of the inside. So the derivative of the inside does a chain rule as well. So we do the derivative. So now I'm ignoring the outside, so ignore this for right now. I am only looking at this value right here. The derivative of this outside part of that is the sine. So derivative of the sine is cosine. Inside part remains the same. Then I multiply by the derivative of the inside. Simplify everything down. Boom, this is what I get. Yes, you can move this to the bottom if you so choose to. Slopes of parametric curves. So parametric curves are defined as x of t comma y of t, and it's differentiable at t if x and y are differentiable at t. So how we find it is basically we find the derivative of the y's with respect to t, that goes on the top, the derivative of the x with respect to t, that goes on the bottom. So I just think y's on the top, t's on the bottom. I find the derivatives of each, not using quotient rule, which is nice, and then simplify it down. So we will do one on the very last page, or I'm sorry, on my examples page. So if you want to look at an example of this, you can.